Morning. Today we're going to be looking at electromagnets and the electric field. There was once a guy, Hans Christian, who discovered that when he placed a compass near a wire with a current in it, the compass pointed in a different direction than when there was no current in it at all. Now, the thing that we need to keep in mind here, which is kind of a little bit goofy, is that in physics, because they did this a long time ago, made a mistake, and we're just going to keep rolling with this mistake, is the following. Current is defined by the direction a positive charge will flow through a wire. So it's, even though the electrons are the ones that are flowing through the wires, we consider it like, what's the positive charge flowing through there? Sorry about that interruption. For me, that was like 40 minutes. For you, a couple seconds. All right, where we last were chatting here was about current. So yes, you notice that when a current was flowing through a wire, the compass would actually change direction. And so here we're going to be learning about a couple of the right-hand rules. So if you've ever wondered why some physics, I guess, students are waving their hands around while doing a test, it's because of the right-hand rules here. So trick to remember when using the direction or finding the direction in a magnetic field. And so there's two different components here. There's the current, and then there is the magnetic field. So we last learned about the electric field being capital E. Capital B is the magnetic field. And so within this first rule here, we're going to represent our current with our thumb and the magnetic field with the curl of our fingers. And one thing to note right over here, very important, if we're looking at drawing and representing things either coming out of the page or into the page, these are the representations we're going to be using. Now, the way that you want to consider this is maybe as an arrow. So the point of the arrow is coming towards you, and so that's why there's this little dot coming towards you out of the page. Or on the other end of the arrow where you have the fletchings going into the page, that's kind of a representation of what that kind of looks like. So maybe that's how you can remember it. If there's a better way, then go for it. But that's what's happening. Out of the page with the dots, into the page with the X or the end of the arrow there. So let's get started then. Let's take a look at a couple examples of what that would actually practically look like. Current is going left through a wire. What is the direction of the magnetic field around the wire? So as we're going through this video, I'd love for you to try along. So stick out your right hand, stick your thumb to the left. So after you've drawn your current going to the left, stick out your thumb to the left, and then begin to curl your hand. So as you curl your hand, above this wire, it's going into the page, and below the wire, it is coming out of the page. And so that's how this is represented right here. So here's the magnetic field, and it's represented in that particular way. On the other side here, let's take a look at number 2. Current of the wire is going into the page. So this time the current of the wire is going into the page, and so I represented that with the blue here. There's an X. So this time you can stick your thumb towards your computer screen. And as you do so, again, curl your fingers, and what you'll notice is that the magnetic field is going clockwise. For the second right-hand rule, very similar. In this case, now your current is the fingers, and the magnetic field is the thumb. So it's kind of almost the opposite. This is in the case of current carrying where you have a loop of a wire. Sometimes you can see them as solenoids, but you see a wrapped wire going around here, so you have a particular current. And if you were to go in the same direction with your fingers as the current is going, what you're going to notice is the magnetic field is going to be pointing towards the north over here. So just like this hand is doing right over here, the magnetic field is to the north. So let's take a look at a couple of examples here. Example 1, current is going counterclockwise through a wire. What direction is the magnetic field within the coil? So what you'll do is try to find a way in which to have your hands curling counterclockwise. And what you'll notice is for that to work, your magnetic field is going to be pointing towards yourself or out of the page. For number 2, the magnetic field within the coil is moving from the east to the west. So it's moving in a western direction. This is the magnetic field, B. What is the direction of the current in the coil? This time you should be sticking your thumb to the left or westward. And if you do so and you begin to curl your hand, what you're going to notice is that your fingers are going to be pointing into the page above and out of the page below. And so that's what number 2 looks like. So when you're dealing with a coiled wire anyways. Let's move on. Magnetic forces. It was in the early 19th century where André-Marie Ampère was studying the magnetic effects of an electromagnet and demonstrated the forces that current-carrying wires have on each other. Here we measure current in either amperes or amps after the scientist, and which is basically the amount of charge passing through a wire in a given amount of time. So 1 amp is the same as 1 coulomb per second. So if you need to break that down, it's never a bad idea to also know what these represent. So when you have an ampere, you know that, okay, that's actually a coulomb per second. I already mentioned that we represent magnetic fields with the capital B, and it's going to be the area around a magnet where another magnet or current carrying wire will experience a force. And so we just looked at a couple examples of where a current can induce a magnetic field, either with a straight wire or a curled wire. And the units for the magnetic field are called Teslas. And 1 Tesla is the same as a Newton per amp times meters. So newtons over amps times meters. If we're to calculate the force on a current carrying wire and a magnetic field, we have a particular formula right over here. And that's because the current carrying wire produces a magnetic field, and we've mentioned that before. If this wire is in a magnetic field produced from some other source, and we're not going to worry what that might be, there will be a force exerted on the wire by the other magnetic field. And through experiment, it was found that the force on the wire can be actually calculated with this particular formula. So your FB is your magnetic force. And remember, B is the strength of the magnetic field measured in Teslas, and the forces are always measured in newtons. Current measured in amps. And then L is the length of the wire. Make sure to measure that in meters. Simple enough, just multiply all 3 of them together. So the longer the wire, the more force that you're going to be feeling from that particular field. The larger the current, same idea there. And obviously, the larger the strength of the magnetic field, the more force the object will feel itself, or the wire will feel. Something to note, we should potentially, I guess, add the sine theta to this particular formula. There are going to be instances where we're going to have to be breaking it into the components, into the x component and the y component, and then calculating as necessary, because the full forces are felt when they're at a perpendicular angle to each other. So when they're at a 90-degree angle to each other, that's when they're going to feel the full force. And if you type in sine 90 on your calculator, what you'll find is that that value is 1. Any other angle for sine that we'll be looking at, so anywhere between 0 and 180 other than 90 degrees, you're going to get a value of less than 1. And so this is going to be where you have the most amount of force based on, I guess, the directions that your field and your current are facing. So just be aware of that if it's not at a perpendicular angle, we will be having to break it into components and then use sine theta to actually calculate what that looks like. Now to the examples. 1.55 meter long wire with a current of 5 amps. Flowing through it is a magnetic field. The force on the wire caused by this magnetic field is 0.375 newtons. what is the strength of the magnetic field it is in? So we have a force, we have a length of a wire, and we have a current. And so with this formula, we just rearrange it by dividing by the current and the length on this side to bring it to the other side here. And then all I did was flip the two sides here. So I normally like to have my unknown variable on the left. And that is what I did. So I divided by current and length. Afterwards, you just plug in your values. Make sure on the bottom here, if you're punching this in, it's brackets 5 times 1.55 brackets. And you get your final answer of decimal 0.484 Teslas. And I guess my final answer could have been decimals. Yeah, exactly that. That's good. So nothing too crazy there. One last thing to mention is that we don't have a direction just yet. All we were asking for here is what is the strength of the magnetic field. In future cases, we're going to be actually looking for, well, what is the direction? Because the magnetic field is a vector, just like the force of the magnetic field is as well. And so we just have to be aware of that normally, if it's asking for what's the magnetic field, you're going to have to include a direction. Here was just what's the strength or what's the magnitude. And so often if it's asking for strength or magnitude, it's just the number or value itself, as opposed to if you're actually saying, well, what is the magnetic field? Then you'd be looking for a direction. So how do we go about calculating a direction? Well, we have a third right-hand rule for a current carrying wire in a magnetic field. To determine the direction of the force on a current carrying wire in a magnetic field, it's important in this case to keep your hand open. In the last two cases, we were curling our hands, and so this one, it's open. We go back to rule 1 in the sense of the current is our thumb, but after that, everything is thrown out the window. So our magnetic field is our fingertips, and the force that is felt on that current due to the magnetic field is our palm. So this is going to just have to be put into memory. So just look at this, go over it, and as we go through some of these problems, try them out yourself. That's going to be the best way to go about doing this. And so if we want to read that one more time, just to really hammer it into your heads, the current is your thumb and it points in the direction of the current in the wire. The magnetic field is your fingers that point in the direction of the magnetic field. And your force is the palm points in the direction of that force. So use the following diagram to determine the direction of the current flowing through the wire. So we have two magnets here that are creating a magnetic field, and it's again flowing from north to south. That is where your field is, and so that's going to be where your fingertips are going to be pointed. All right, so start with that, pointing your fingertips to the left. And then afterwards, the next thing is look at the current. The current is facing downwards. Or sorry, that was what we were actually supposed to determine. So the next thing is you need to try to get your palm facing into the page. And so the only way in which to do that is to flip your hand around. So if you were like me, you had your palm facing yourself. So now you want to flip it so the palm is facing the computer. And in that case, now your thumb is pointing downwards, and that represents the current. So we have determined that the current is facing downwards. We're going to attempt to use the right-hand rule for the first two questions here and beyond. What is the direction of the force on a wire if the current flows east? So we got current flowing to the east over here. And the magnetic field is directed upwards. And this is going to be kind of weird because we're dealing with multiple dimensions here. So if we're going east over here, and if we would be representing this like up as north, this is south, and this is west, we're going to need to look for something else to actually say, well, okay, what could be up, what could be down? So I believe on my notes over here, I had up just being a dot. Maybe need to use something that looks a little bit darker there. And down being like this. So the magnetic field is directed upwards. So we're going to represent it with our circle and a dot. Now it's your turn to give this a try here. So stick out your thumb to the right And the next thing you want to do is you want to have your fingertips pointing upwards. And what you'll notice is your palm is going to be facing you. And so if we're looking at direction wise, if your thumb is east, then facing you is going to be south. And so what is the direction of the force? The force is going to be south. Number 2, what is the direction of the current flowing through a wire if the wire would experience a force towards the east? So this time we have a force towards the east. When in a magnetic field pointing down. And so before we represented down like this, so here is our magnetic field. In this case, we're going to have our palm facing east or to the right. Again, do it based on your perspective here. Secondly, let's try to have it so that our fingertips are pointing down. So palm to the right, fingertips pointing down. And where do you notice your thumb is pointing? Which means the current is going to be facing south. Number 3, a wire is 1.25 meters long and has a current of 3.25 amps facing north flowing through it. So we can already draw our current facing north. The current carrying wire is in a magnetic field with a strength of 0.465 Teslas up. And so again, it's going to be a field that's up. So right off the bat here, we're going to be being asked to find the magnitude and the direction of the force. So in this case here, look at that, magnitude and direction. We need both. So let's again start with figuring out, well, what direction is our force going to be? And so stick your thumb north. So start with that. Next, stick your fingers up. And so your fingers are up and your thumb is north. So by north, it's kind of like pointing into the computer screen. Fingers up. What you'll notice is the force is going to be pointing east or to the right. As for the magnitude, use your formula. Force is equal to the magnetic field multiplied by your current and the length of the wire. And so we have all these. This is already in meters, this is already in amps, and this is already in Teslas. Multiply those three values together. And what you'll end up getting is a value of 1.89 newtons. We already determined our direction was towards the east, and that's number 3. Number 4, we're asked to give the direction of the magnetic force acting on each conductor in the following diagrams. So you do have some magnetic forces traveling from the northern side over here to the southern side. And so we could draw that for all of them right over here. North to south. This is going to be our magnetic field, right like that. That's our magnetic field. And next, what we have is the current right over here. So the current is represented coming out of the page. So start with putting and sticking your thumb towards yourself and having the fingertips, your field, pointing upwards. What direction is the force? If you said to the west, you are correct. For B, in this case here, we now have our magnetic field pointing south and our current is into the page. So this time you want to stick your thumb away from you, kind of into the page, and you want to have your fingertips pointing down. what way is our force? It will be west again. For C, I'm not going to tell you what to do, so I'll just state where your finger is going to go for your magnetic field. Where is the thumb going to go for your current? And what direction is your palm facing? If you said to the east, you're correct. Number 5. At New York City, the Earth's magnetic field has a vertical downward component. So we're going to have a vertical downward component being the magnetic field of a very small value. What is the magnitude and direction of the magnetic force? So we're looking for the magnetic force here on a long straight wire that is 6 meters in length and that carries a 28 amp current due east. So we have this being east over here. And this is our current. So just start by sticking your thumb to the east, sticking your fingers downwards, and this is going to be real difficult to do with your hand. You're going to have to contort it a little bit. So if you're working it out properly, your thumb towards the east, your fingers down, that's going to be tough to do. I have to use even my left hand to get my right hand to do what I want to do. What you're going to notice is that this direction for your force should be north. All right. As for the calculation, we do remember the formula. It's just this force is equal to your magnetic field multiplied by your current times your length. And again, we have all three values. We have a magnetic field of 5.2 times 10 to the negative 5. We have our current of 28 amps, and we have our length of 6 meters. Final answer should be 8.74 times 10 to the negative 3 newtons, and that's in the northern direction. Number 6. A square coil of wire containing a single turn is placed in a uniform 0.25 Tesla magnetic field, as the drawing shows. Each side has a length of 0.32 meters, and the current in the coil is 12 amps. The direction of the current is going in the clockwise direction as the arrows point. Determine the magnitude and direction of the magnetic force. So again, we're going to be looking for what is our magnetic force FB at the wire AB, at BC, at CD, and at AD or DA, whatever you want to call that. Let's start with AB. We have a current, so current is represented with the thumb. And so start by placing your thumb towards the right. Next, we have a field that is in the upwards direction. So place your thumb to the right, your fingertips upwards. And what you notice is that the field at this point here is coming out of the page. All right, let's do the opposite one right off the bat. Let's go straight to CD. So in this case here, all we're going to be switching is the direction of our thumb. So the field and our fingertips are still pointing upwards. Now our thumb is just pointing to the left. And if we do it correctly, we're going to have force of the magnetic field is going to be into the page. Now, let's take a look at BC and AD for a moment here. There's going to be a problem here. Specifically, if you're looking at this one, our current and our magnetic field are pointing in the same direction. And I mentioned that earlier that if it's not at a 90-degree angle, you're going to have less and less total force to the point of when it's exactly parallel here, there's no perpendicular forces at all at AD. And so there's going to be absolutely no magnetic force. So there's going to be a magnetic force of 0 at this value here. And similarly, this one is a full 180. And same thing, there's going to be no perpendicular forces over here. There's nothing in this direction. It's only going up and down here. So again, our magnetic force over here is going to be equal to 0 as well. So simple enough, we've already calculated the magnitude for AD and BC, and there's no direction because again, we have a value of 0 in either case here. So all we now need to do is determine what our magnitude of our magnetic field is for AB and CD. And since it's a uniform magnetic field with every length being the exact same value, our magnitude is going to be equal for AB over here as well as CD. And so again, just plug it into your formula and you should be good to go. So we have 0.25, we have 12 amps and 0.32 meters. And what you should end up having is a value of 0.96 newtons. And at AB, it's coming out of the page. And at CD over here, it's going into the page.